Now the next speaker of today is Vasileios Fragkos. He's from the University of Stockholm, and he'll talk about lessons on quantum gravity from gravitationally induced entanglement. So thanks, Vasileios. The floor is all yours.
Yeah, thank you very much for the introduction. So I would like to talk about a recent paper that we put on archive with my supervisor, Igor Pikovsky, and a collaborator, Michael Kopp. And it's related to the gravity-induced entanglement proposals. In 2017, there were two PRL papers that appeared simultaneously in 2017, yeah. And the authors claim to test some quantum aspects of gravity in a tabletop experiment. On the right top side, you can see the figure. So the basic idea is that you have two masses, you put them in a spatial superposition, you allow them to, you embed the spin in a specific realization, you embed the spin degree of freedom, you allow it to interact gravitationally, and then you recombine the beams and do some spin correlation measurements to verify if entanglement has been generated through gravity. And the basic, the claim of this proposal is that if an entangled state is generated and we assume locality of interactions, then by using the LOCC argument, you have to conclude that the gravitational, the underlying field should be quantum mechanical in nature. The notion of locality is a very central notion in these proposals. And for example, in 2017, the original proposal by Marletto and Vedral, they define locality in this way, like assuming having three systems, A, B, and C, and you allow A and C and B and C interact, but not A and B directly. You can think as A and B as the masses, and C, let's say, the gravitational field or mediator. Immediately from this, there are some caveats. And one caveat is the fact that in order to compute the phases in the original proposals, the authors used the Newtonian potential, which is non-local. So the experiment is within the Newtonian limit, let's say. And the locality in these proposals is assumed. So in order to make conclusions about the quantum nature of the gravitational field, you have to assume that quantum gravity is a local theory, and this is not tested in the experiment. So the goal of our paper was exactly to try to see how entanglement is generated in different formulations and in different theories, and draw some conclusions about, depending the initial assumptions one is willing to have. And in particular, we focus on two ways to let's say, ways to see the problem. First, in the non-relativistic limit, and then assuming that this Newtonian theory is a limit of a relativistic theory. In the first case, we're going to talk about Newtonian theory, and it's what we call a minimal interpretation of the GIE. And in the second case, we're going to see that weak field quantum gravity we can understand entanglement within weak field quantum gravity in a local and a non-local description. And that's actually the take-home message that from this talk, that weak field quantum gravity admits both local and non-local formulations. So we can see that LOCC has limited ability to verify the quantum channel. It's unambiguous. And, but we're going to conclude that there is some novelty in this experiment, and it's exactly gravitating source masses in a spatial superposition. But still, there is a small caveat there that we're going to talk about a bit about cosmology and see that source mass quantization, we already have some indications by CMB observations that this theory is quantum mechanical. So let's start with the Newtonian theory. One first thing is, okay, the GIE works in the Newtonian limit, and we talk about the Newtonian potential. So how do we make sense of a Newtonian potential in a quantum superposition, on a spatial superposition? So a way to understand this problem is by reformulating the n-body problem, so having n gravitational interacting masses, to a second quantized language, where psi is a field operator which creates a particle at position x. And we see that the Newtonian potential phi appears in the Hamiltonian, which satisfies this Poisson equation, where the source on the right-hand side is psi dagger psi. Solving this Poisson equation, we get a solution for this Newtonian potential phi as an integral over d3x prime. And we see that if we can put expectation values on the right-hand side, then we can assume that also the field, we end up with a field, a gravitational field, which is classical. And this is the case, for example, in the cow experiment, where the source is the gravitational field of the Earth. So we treat the field as a classical field. The neutrons get a phase in the cow experiment, which is sourced by a classical field. But this is not the case in the GIE, because we have masses in a spatial superposition. So mean field description is inadequate. And within this framework, with this Newtonian theory, assuming standard quantum mechanics, we see that you can understand the GIE in this kind of framework. And what it tests is just sources in quantum superposition, gravitating sources in quantum superposition. Now, what happens if we assume that a relativistic parent theory, then for weak field quantum gravity, we have here two formulations, a non-local one and a local one. In the non-local case, you can see that you can expand the metric around the Minkowski background, decompose the fluctuations h, mu, nu in terms of scalar vectors and tensors, fix the gates, and end up with an interaction Hamiltonian, which contains a first term, which is just the usual gravitational waves, the transverse traceless part of the metric, 2 degrees of freedom, which is subdominant in the GIE because the GIE is not in the regime where gravitational radiation is relevant. And on the right side, we have this big term here, which is entirely sourced by matter. So every function that appears there is a function of the stress energy tensor. So in this picture, entanglement is generated non-locally once you remove the redundant degrees of freedom. An equivalent formulation, but this time local one, is if you quantize all the degrees of freedom from the very beginning, so you quantize all the 10 degrees of freedom of the metric, and then you have 10 creation and annihilation operators, which then, this is work done by Gupta in the 50s and 60s, both for QED and weak field gravity. And you can eliminate imposing some conditions on the Hilbert space, eliminate some redundant degrees of freedom. But if you do the calculation in this picture, then you will see that entanglement is generated locally via the exchange of some auxiliary fields, some particles, but not the standard spin to transverse traceless part. There is also a third way to relativistic formulation. This is a so-called absorber theory. And the initial motivation was for quantum electrodynamics in the 40s and 50s. And Wheeler and Feynman tried to reformulate electrodynamics, but this time by replacing this standard coupling J mu A mu of QED with the other Lagrangian, which has only masses described by this J mu current. And so this theory there were quantum version of this Feynman-Wheeler by Hoyle, Narlikar, and other people in the 60s and 70s. And it's very interesting that they could, all the predictions of conventional standard QED can be also predicted within the absorber formulation. This in the Lagrangian, this delta function that appears is in terms of the advanced retarded propagators. And it's a causal theory, but it's non-local. That's the important thing, that QED, the Wheeler-Feynman absorber theory, is non-local in space. So for weak field quantum gravity, there exists an absorber theory. And again, in the same spirit as in the QED, you can remove the mediators and end up with a theory which is non-local in space, and it's sourced only by matter. There is no the concept of field in both weak field quantum gravity and QED in the absorber formulation. So in this picture, the entanglement is generated non-locally, and there are no mediators to be quantized. Of course, an open question.
You have 2 minutes.
Yeah. So there is an open question for full GR. It's not, we don't have an action at a distance formulation, and we don't know if full quantum gravity is a local or non-local theory. So here, just to summarize how entanglement is generated, it's important that you can choose a local formulation, and this is the case done, for example, in these papers by Bose, Christodoulou, Marletov, et al. You can use that formulation and derive the effect in a local way, but also it can be derived in, within a non-local framework. And it's important also that locality is not dictated by relativity, in the sense that absorber theory or the non-local formulation of weak field quantum gravity are causal theories. So the take-home message is that the LOCC is ambiguous, and you cannot uniquely infer quantization of mediators because there are also non-local ways to generate this entanglement. And the same, of course, holds for QED. You cannot infer the existence of photons for having the electromagnetic analog of the GIE. As a last remark, I would like to mention that in cosmology and within the inflationary paradigm, if you write down the standard cosmological perturbation theory, you end up with a Poisson equation for the field phi, which is a so-called Bardeen potential, and it's written in terms of the scalar functions of the metric. And this Newtonian potential sources the temperature fluctuations of the CMB. So the fact that we have tested the temperature isotropies to such an accuracy indicates that probably the scalar part, the constrained part of the metric is quantized. And it's the same regime that GIE probes. And let me end with the conclusions. So here we see different theories. In some of them, you can see that there are no mediators, and the entanglement is generated non-locally, whereas in the local formulation, entanglement is generated locally and LOCC applies. But this comes with a cost for the local formulation, that someone has to elevate these auxiliary ghost fields to physical entities. And recently there was some work by some people who tried to move towards that direction. So the take-home message is that weak field quantum gravity admits both local and non-local formulations. So LOCC is less powerful than initially thought, because exactly because of the notion of locality, which within standard physics that we know seems to be ambiguous. Also, the constrained part of weak field gravity has been indirectly tested by CMB observations. And the novelty of the GIE is that it probes masses which gravitate, and they are delocalized, they're in spatial superposition. Thank you very much.
Thank you, Vasileios.